Welcome to the video for chapter 4.4. So 4.4 is all about biochemical reactions. So we're going to talk about some chemistry. Not in a lot of detail as if you had taken a chemistry class, but in a little bit more detail than we've talked about in other classes. But first, let's start with a review question. So review question number 1 says, which level of protein structure consists of peptide bonds? Is it the primary structure, A, B, secondary structure, C, tertiary structure, or D, quaternary structure? So take a minute, pause the video, and see if you can find the answer. Okay, so the answer to this question is A, primary structure. So if you remember from the previous lecture, the previous video, peptide bonds show up in the primary structure. This is what holds the sequence of amino acids together. So the answer is A. Okay, let's do a slightly different review question. So this is review question number 2. Okay, it says, what is the best explanation for the molecular motion, so how the molecules are moving, occurring in the diagram below? Is it A, the gray molecules are hydrophilic and do not dissolve in water? B, the gray molecules are hydrophobic and do not dissolve in water? C, the gray molecules contain ionic bonds that dissolve in water? Or D, the gray molecules are hydrophilic and repel water molecules? Okay, so take a second, pause the video, flip through some notes if you need to, see if you can't find the answer. Okay, the correct answer for this question is B. The gray molecules are hydrophobic and do not dissolve in water. Now, this would be an example of a good question to know for the next exam, because this is one that can be easily flipped around. Okay, and the key to being able to answer this question is knowing the definitions of both hydrophilic and hydrophobic. So hydrophilic, this is our polar molecules. Okay, so if hydrophilic is polar, it means it loves water. Okay, so it's going to interact with water, meaning it's going to dissolve in water. Okay, so we know immediately, based on the definition of hydrophilic alone, that A can't be right, because if it's hydrophilic, it is going to dissolve in water. And we also know that D is not going to be right, because hydrophilic means water loving. It's not going to repel water molecules like hydrophobic is. Okay, hydrophobic, this is going to be our nonpolar molecules. Nonpolar molecules and water molecules, which are polar, don't interact well. Okay, remember our like dissolves like. Okay, so hydrophilic is going to interact with them. Hydrophobic does not, which is why B is correct, because this is the correct definition of hydrophobic. Now, what about C? Okay, if the gray molecules contain ionic bonds that dissolve in water, this would be correct if it did have ionic bonds, but what we would see is we'd see much smaller molecules in this picture, if we're in the gray, and then we would see each of these individual atoms separated and surrounded by water molecules in this picture. So C is kind of the weird one that stands out. When we see weird answers like this, it's either going to be the correct answer or it's not going to be an answer at all. So in this case, C is not an answer at all. Okay, so in chapter 4.4, we're going to talk all about biochemical reactions. So our objectives for this section are you need to be able to explain energy. What is it? And you need to be able to describe something called entropy. And you're going to have to use both of these terms to determine the direction a reaction is going to go. Okay, and you need to be able to explain how enzymes catalyze reactions and the various factors that can be used to have enzymes increase the rate of reaction. Okay, so we got to do a throwback to physical science. We got to talk about energy. We got to talk about work. Okay, so in science, we define energy as the ability to do work. Now, if you remember from physical science, work is defined as the transfer of energy needed to have a force move an object. Okay, so energy is literally the ability to move things through force. Okay, so when we talk about energy, we have to have a mini thermodynamics lesson. We have to talk about the laws of thermodynamics. Now, the first law of thermodynamics, you know as a different name. You know it as the law of conservation of energy. So the first law of thermodynamics states that matter and energy are neither created nor destroyed. Okay, both matter and energy are held constant throughout the universe. We can transfer them, we can transform them, but we can't create or destroy them. Now, the second law of thermodynamics states that in all energy transformations, some energy is going to become unavailable or unusable to do work. Okay, so it's not going to be able to move things. And when this happens, this energy is lost as what we call entropy. Entropy is just a fancy word for how disordered or chaotic a system is. Okay, so let's talk about this for a second. Let's talk about the different states of matter. Since physical science, we're all experts on the definitions of our states of matter. So let's talk about solids first. So solids are rigid. Okay, they have a defined shape, they have a defined volume. Okay, if we talk about this in terms of energy, okay, solids don't the particles that make up a solid don't have a lot of energy. Okay, well, if our particles aren't moving very far and we have a defined shape and we have a defined volume, that means that solids are highly ordered. They're not chaotic, so they actually have very low entropy. Now, if we take a solid and add energy to that solid and to the particles in it, then we're going to transition from the solid state to the liquid state. Now, liquids have a characteristic where they flow. Okay, they still have a defined volume like solids, but they're going to take the shape of their container. They don't have that rigid structure. Because they don't have that rigid structure, they're more disordered or more chaotic than solids, which means they have more entropy. Okay, so if we go from liquids to gases, okay, we've added more energy. The particles are moving even faster. In fact, they're moving so fast that attractive force that holds molecules together in a substance isn't there. So they're not next to their neighbors. So individual molecules are spread out. So gases can flow like liquids, and they also take the shape of their container, but the difference is because their particles have so much energy, they can take up the volume of their container as well. Okay, they are a lot more disordered, they're a lot more chaotic, so out of the three states of matter, entropy is going to be highest in gases. Okay, so if you notice the common thread here, as we go from solids to liquids to gases, what happens? Well, we're going to increase energy as we go from solid to liquid, and we're going to increase energy as we go from liquid to gases. So a lot of times, an increase in energy is going to lead to an increase in entropy, or an increase in disorder or chaos. Okay, entropy is one of my favorite scientific concepts because literally it's a measure of chaos, or how chaotic a system is. Okay, so let's think about this in terms of chemical reactions. Okay, if you remember, the things that go into a reaction, we call them reactants, and the things that come out of a reaction are products. Okay, so a lot of times when we are doing a chemical reaction, we are going to have an energy change. Now, how this energy change happens depends on the type of reaction, but we can talk about this in general terms. So all the reactants in the system are going to have what is called usable energy. Now, if you remember, in chemicals, where do we store the energy? Well, energy is stored in the bonds of the molecule. Okay, so when we break the bonds of the reactants, we release a bunch of energy that can be used. And all that energy is usable energy. Okay, so we're going to have an energy transformation. If this was a chemical reaction, we're going to make something new. We're going to break the bonds in the reactants, and we're going to start to make new bonds to form the products. Okay, so that's our energy transformation. But the thing is, when we start to make bonds, making bonds require energy. Okay, so we're going to take all this energy here from breaking the bonds and putting it into making the bonds. Now, in this energy transformation and going from the reactants to the products, we are going to have some of this energy that's still usable. This is our free energy. This is what's going to go into the bonds. And then we have what's called unusable energy. This is going to be our entropy. So a lot of times when we have an energy transformation, we're going to lose a little bit of energy to heat, and that heat's going to become unusable. Okay, so if we think about this in terms of metabolism and energy production, we are going to take an organic compound, so our things that are made mostly of carbon, so our food. That organic compound is going to be broken down into individual glucoses. Okay, they're going to go into cellular respiration, where cellular respiration is going to literally break all the bonds in the glucose and harness the energy stored in those bonds. They're going to transfer them using oxidation reduction reactions or redox reactions. We'll talk more about this at the end of this lecture. Okay, so it's going to take these redox reactions, and it's going to take that energy from the glucose, and it's going to go and store that energy in our ATP molecule, which is the molecule that cells can use for energy directly. Okay, so if energy transformations power life, what does this really mean in terms of reactions? Okay, so we have our water wheel here. Okay, so think about this like a canal where we have this part of the canal that's up and this part's down, and we have the water wheel in between. Okay, so we have the reactants on this side where we have a higher level of water. We can think of the water as energy in a reaction. Okay, so in this case, the energy of the reactants is going to be greater than the energy of the products. Okay, so what's going to happen is that our water level here is high and it is low here. Things in science like to go from an area of high concentration to an area of low. So the water is going to want to flow from here down to here. Now, as it does that, what's going to happen is it's going to flow down and it's going to push this water wheel and cause this water wheel to start turning, which is going to allow the water to come to this part. Okay, so in terms of reactions, this is a reaction moving forward. The bigger the water level difference or energy difference, the faster the reaction is going to happen. Okay, so this is we're going from high to low. Now, as the reaction continues, our products, so our output is going to increase. So we're going to make more and more products. So our water here is going to fill up, fill up, fill up. And as the water gets higher, what actually is going to happen is the reaction is going to slow down as our number of products increase. So that our water level here increases. So we might get to a point where our inputs, so our reactants equal our products. This could stop the reaction altogether. We could come to a part where we have very little reactants and a lot of products. Now, when this happens and the products have a higher energy or higher level than the reactants, okay, so we say our water is about right here. So it's going to be above the level here. What's going to happen, so instead of pushing this way and turning the wheel this way, okay, what's going to happen is all of our products have built up on this side of the wheel. What's going to happen is they're going to push back on the wheel, and they're going to push the wheel down and backwards to the way it was turning, and it's going to reverse the reaction, so the reaction is going to go backwards. This only happens if the level of products gets too high. But remember, the bigger the difference between the level of reactants and the level of products is going to mean that our reaction is going to move faster. Okay, so as we go here and push the wheel, this is going to happen very quickly. But as the amount of products rise up, okay, this process is going to slow and even stop. Okay, this is how we can tell the direction of the reactants, is what is our level of reactant compared to our level of product. We do this in terms of energy. So how much energy do our reactants have versus how much does our products have? Now, if you remember from 201, This graph should look familiar. Okay, so when we have energy that in the reactants that's higher than the products, we can classify this reaction as spontaneous, meaning that it's going to move in a forward direction. Okay, it might be a slow reaction, but what's going to happen is that reaction is going to continue and go through what's called a high energy transition state. A transition state is when we have made the reactants unstable. Okay, once the reactants are unstable, we can start breaking bonds. And then once we can start breaking bonds, so this is the transition state, we're going to start breaking them. Once we start breaking bonds, we have energy and we can start forming bonds. Okay, so a spontaneous reaction is going to pass through this high energy transition state to make products. Now, spontaneous reactions happen if the reactants have a higher energy than products. Okay, so the transition state of a reaction is found at the top of this hump or hill. Okay, now, in order for a reaction to happen, we might need to add a little bit of energy to the reaction. Sometimes we do this in form of heat from a different reaction, so that heat's going to come and give us that little bit of energy boost we need to get to our transition state and allow our reaction to happen, because our reaction can't happen until our reactants become unstable and are ready to break the bonds. Okay, so this hump in this diagram is what we call the activation energy, okay, or EA. Okay, so this is the amount of energy needed to reach this transition state and have the reaction happen. Okay, so this is the diagram for a spontaneous or exergonic reaction. We're going to release energy, is what this means. Okay, once we can get to this transition state at the top of the hump, our reaction actually happens pretty quickly. But how fast we get to the top of this hump depends on the reaction. Now, if only we had a way to speed that process up, to lower the activation energy so we can go a little bit faster. But first, let's talk about what it really means to have an activation energy. So let's refer back to a reaction that we all know. Okay, the combustion of methane. So CH4 is methane, we add it to oxygen gas, the reaction happens, we make CO2 and water. So we need that little bit of energy in order to ignite the methane and cause it to start to combust or burn so we can start making our CO2 and more water. So if we have a gas stove, a lot of us have gas stoves that we cook on. Okay, in order to get the flame on our stove with our natural gas, is we're going to need that little extra spark. Okay, so the igniter in our stove is going to be the amount of energy needed to get to the top of that activation energy hump and allow the combustion of methane to happen. Okay, so that spark is going to give us the energy needed to start to break the bonds in the methane molecule and the oxygen molecule so that they can then be recombined and new bonds can form to make carbon dioxide and water. Okay, so how can we make our reactions go faster? How can we lower this hump? How can we lower this activation energy? So in organisms, in biochemistry, we use what is called a catalyst. Okay, catalysts are things that speed up our reaction, but they are never part of the reaction. Okay, which means they're never consumed. Okay, so the amount of catalyst you put into a reaction, the same amount is going to come out, and it's not going to be changed. It's not going to be consumed. Okay, so in biology, our biological catalysts are proteins called enzymes. Okay, so enzymes are going to lower the activation energy. They're going to lower this hump in our diagram and allow the reaction to happen more quickly. Okay, so remember, in our molecules, our energy is stored in those bonds, and in order to access that energy, we need to break those bonds in order for the reaction to happen. So what happens is when we have an enzyme, it's going to reduce the amount of energy we need to have the reaction happen. Okay, so our reaction can happen more quickly. Okay, enzymes are almost always proteins. We do have some enzymes that are called ribozymes, but we won't talk about those in this class. Okay, so how do enzymes lower activation energy? So enzymes can lower activation energy in one of four ways. Okay, our enzymes can take two substrates. So enzymes are going to have little pockets where a substrate or a molecule will be able to sit. Okay, each enzyme is specific for a specific substrate. Okay, a lot of enzymes can only do one thing. So it can take two separate substrates, okay, and bring them into contact with each other so they can position them so that the reaction can happen. Okay, they can take one thing and they can put it in the enzyme and it can twist it. We call this contortion. So we can add stress to that bond when we twist it, and what's going to happen is the enzyme's going, once we add stress, it's going to be easier to break it apart because our bonds aren't stable. They're more easy to break when we put them underneath stress. So enzymes can do that. So they can twist the molecule, put it underneath stress so bonds break more quickly. This will lower the activation energy and get us to that transition state more quickly. Okay, so the area that the substrate can bind, we can change the environment of that area. We can make it acidic, so acids make it so bonds are less stable, so they're easier to break. We can make the active site, that spot where it sits, polar. Okay, remember polar molecules like polar conditions. So we can make something unstable if it's polar by having a polar condition, or we can have it be not a non-polar condition. We can have it positively charged, negatively charged. We can provide the environment needed to cause that reactant, that substrate, to become unstable. Okay, and the fourth thing our enzymes can do is that they can temporarily bind to the substrate themselves. Okay, and this is going to make the substrate unstable. And when it's unstable, the bonds are easier to break. Okay, and then we can start the reaction. Okay, one of the things that you have to know, okay, enzymes do two jobs. They lower activation energy, and they are never consumed in a reaction. So when we get done with a reaction that an enzyme is catalyzing, the enzyme is perfectly functional and it can go and start the reaction over again with a new substrate. Okay, so it's there and able to continue its job with another molecule. Okay, so let's talk about enzymes. Enzymes, like all proteins, work best at a specific temperature. We call this the optimal temperature. Okay, because shape denotes function, if we change the shape of the protein, we can make it either have a new function or become broken and not function at all. Okay, so one of the ways that we can change the shape of a protein is to heat it up. We can change the temperature. So if we increase the temperature, we can break the bonds and we can reshape the shape of the protein. And this is what we call denaturation, where changes in the protein structure leads to changes in function. So if we break the bonds and we change the shape, a lot of times this is irreversible, meaning that we can't go back to our original shape. Okay, we can have chemicals that do denaturation, so we can have changes in pH, which we'll talk about in the next slide. But when we're going back to temperature, we can decrease the temperature, and what's actually going to happen is we're not going to break the enzyme, we're not going to break the protein, but we're going to make it inactive because it doesn't function at lower temperatures. So all of our proteins in our body are going to function at that 97.3, 98 degree Fahrenheit range, where that's our body temperatures. Okay, that 36 to 37 degrees C. Now, with denaturation with proteins, we have to be very careful, and this applies to our proteins as well, because once you go outside this range that these proteins function at, they start to denature. And a lot of these ranges that proteins function at are a very small range. They're not very broad, so we can go outside of that optimal temperature range very quickly. Okay, so every living organism has enzymes. So bacteria that cause infections, our pathogens, have have enzymes as well. So one of the things that your immune system does is when you get an infection, it's going to give you a fever. So it's going to kick up your internal temperature. And that's because your immune system is going to have your body attempt to cook those proteins so that they denature. Now, one of the problems is a lot of our pathogens that cause infection work at the same optimal temperatures as our own proteins. So as our fever increases, we also have the chance of denaturing our proteins. Okay, so when you think of denaturing, you can think of scrambling eggs. Okay, so when you scramble eggs, you're going to have the clear white and you're going to have the yolk. So once you start to scramble it, the proteins in the egg white, the albumin, are going to start to denature. So it's going to change color. It's going to go from clear to white. Okay, this is an irreversible process because we can't reverse scrambling an egg and have it go back to liquid form after we've made it a solid and cooked it. Okay, so the same thing happens with enzymes. So bacterial enzymes and our enzymes work about the same temperature. So if your body kicks you up to a high fever, say 103 or higher, you got to be very careful. In fact, if you have a fever of 103 degrees Fahrenheit that lasts more than 3 days, you probably should go to the hospital because something's seriously wrong. Okay, most average fevers are around 100, 101 degrees Fahrenheit. So when your fever goes too high, not only are you denaturing your bacterial enzymes, you are denaturing your own enzymes. So what's going to happen is you are literally going to start to cook your brain. So the proteins in your brain are going to start to denature. A lot of times when people have really high fevers, they get a little bit delusional. They get these fever dreams, and that's because they're literally cooking their brain. Okay. In fact, if you have a really high fever, say like 105 degrees Fahrenheit, the first thing that the hospital is going to do if you go in for a fever that high is they are going to try to bring your temperature down so you don't denature the proteins in your brain. Because when you denature the proteins in your brain, when you accidentally cook your brain with a fever, it's going to cause some pretty bad brain damage that's going to have side effects that you can't fix. Okay, so one of the first things we do is we try to cool the individual down and bring their fever down to a more manageable level. Okay, so the other way that we can denature proteins and cause them not to work is to use pH. So we can make it an acidic condition or a basic condition. So just a reminder, pH is the logarithmic scale that we use to measure the concentration of hydrogen 1 plus ions in solution. Okay, so the more H plus you have in solution, the lower the pH, the more acidic you are. The more basic you are, the less H plus you have. Okay, so the higher your pH. Okay, so you don't need to know how to calculate pH like we do in chemistry, but what you do need to know is how we use this pH scale, so this 0 to 14 scale, and how we use it to classify something as acidic or basic. Okay, so anything with a pH of 7, so around here, okay, this is the pH of pure water, meaning that we have equal amounts of H plus and OH minus in our water molecule. Okay, pH of 7 is neutral. We're neither an acid nor a base. Okay, once our pH goes below 7, this is going to make it acidic. Okay, so your urine and your saliva are slightly acidic. Makes sense for your saliva because it's literally starting to break down the food you've eaten. Your stomach acid, your gastric acid is going to be around a pH of 2. Your stomach lining is going to secrete hydrochloric acid that's going to have a pH of 1. Okay, so anything that has a pH of 7, we usually think about 6.8 or lower, is going to be classified as acidic or an acid. Now, conversely, if we go above 7, usually we think 7.2, anything above 7.2 is going to be a base, meaning that our concentration of H plus is getting smaller, or we don't have as much of it, so our pH is getting bigger. I can't really think of any of our body fluids that will have a pH of greater than 7, but I can look that up for you. But you do need to know these ranges. 7 is neutral, less than 7 is acidic, more than 7 is basic. Okay, so let's talk about a real life example of this, and let's talk about what happens when you have CO2 in your bloodstream. So we know if we are regularly breathing, we're breathing in oxygen and we are breathing out CO2. Okay, so regular breathing, we're going to have pretty neutral pH in our blood. Okay, but the thing is with carbon dioxide, if you mix it with water, it's going to make what is called carbonic acid. Now, if you hold your breath, okay, so you're not breathing any oxygen in, your CO2 is going to continue to build up, and it's going to react with the water in your bloodstream to form this carbonic acid, and it's going to literally acidify your blood, and your blood can cross the blood-brain barrier, and so it can start to affect your brain a lot like the temperature can start to cook your brain in a fever. Okay, thankfully, when you hold your breath, we can only hold our breath for so long without passing out. Passing out is kind of a way to reset ourselves and get ourselves breathing again when we hold our breath for too long. Okay, so it's a built-in mechanism to make it so that we don't hurt ourselves. Now, conversely, if you start to hyperventilate, you're bringing in a lot of oxygen and you're releasing a lot of CO2. In fact, you're losing CO2 so quickly, the pH of our blood is not going to stay around neutral anymore. It's going to become basic. Okay, so our pH is going to increase. Okay, and this is going to lead to you fainting and passing out and seizures. Okay, so when that happens, usually you stop hyperventilating, your system re-regulates itself and goes back to the normal. So you're going to have a neutral pH for your blood. This is an example of how something so small as increasing the concentration of one gas can affect a bunch of different systems. So if we are too acidic, we're going to affect our proteins. If we're too basic, we're going to affect our proteins. We have that really narrow window around neutral where everything works the way it should. Okay, so this is our last slide in the lecture, and this is kind of an introduction to an idea. So when we talk about how we move energy in a reaction, usually we're talking about how we move electrons. Okay, when we move electrons, we call these oxidation reduction reactions or redox reactions. Okay, so redox reactions are going to transfer electrons, and the electrons are going to act as energy. Okay, so we're going to talk about this more in a different lecture, but we need to know the basics. So when we have an oxidation reduction reaction, these are what we call paired reactions. So we have an oxidation reaction, and then we have a reduction reaction. Now, when we're talking about redox, I like to think of the mnemonic oil rig, okay, because this is going to tell me what's happening to our electrons. So oil rig stands for oxidation is the loss of electrons, okay, so oxidation means we lose electrons. And reduction is the gain of electrons. So reduction means we're going to gain electrons. Okay, so since these are coupled reactions, we cannot have reduction without oxidation, and we can't have oxidation without reduction. Okay, so we're going to have compound A here, and it's going to have these 2 electrons. They were added to it. So compound A right now is reduced. Now, if we remove the electrons from compound A and give them to compound B, what happens now is because we removed electrons, A has lost electrons, so A is now oxidized. B, who didn't have electrons before, was oxidized, and now that we have added the electrons to it, it's going to be reduced. Okay, so oxidation reduction reactions are how we move energy through a system through electrons. Okay, we need to know oil rig, and we need to know what reduction and oxidation mean. Okay, we'll talk more about this process in a few lectures when we really get into redox reactions with things like cellular respiration and photosynthesis. Okay, that is chapter 4.4. Okay, so we've talked about biochemical reactions and how life requires energy and how it gets and transforms energy. So our 2 laws of thermodynamics. We've talked about enzymes. We have talked about how enzymes can lower activation energy, and we've talked about how temperature and pH can affect proteins. Okay, so we will see you all in the video for 4.5.